So this was the problem that I gave everyone during class and asked you guys to work on this. So I'm going to show you the solution, but understand that I'm going to show you two versions. The first one is going to be the more accurate way to do this calculation because we are going to account for the change in the volume. So we're starting with 4 liters and we're going to add sodium hydroxide, and so that volume is going to be plus X, which is the sodium hydroxide solution. And so that's going to be the more accurate way. The second way that I'm going to show you is where we will realize that this X right here is small in relationship to the volume of 4 liters. And so we kind of just forget about the change in volume and just assume that we're still at 4 liters because we're adding so little of the sodium hydroxide. So let's start with the more accurate way. And in order to do that, we need to first understand, we have to write down the equation. So we have the acetic acid that I'm just going to represent by HA, and we are going to add hydroxide. And then at equilibrium, that will convert into the conjugate base, which is our acetate, and that would make water. So we set up our equation, and then let's start by the initial. Do an ice table here. So initially we have 0.134 molar of the acid. We're going to add X amount of our base to that solution, and then we started with 0.04 molar of that, and we don't need to worry about water, right? So the change is the base is going to react with our HA. So for every mole of hydroxide, we're going to lose a mole of HA. And then we're also, when we add the hydroxide to the solution, we're going to use that hydroxide. So that's going to disappear. And then for every mole of hydroxide added, we're going to generate another mole of our conjugate base. So at equilibrium, what we're going to have happen is we have 0.134 molar minus X. Those two X's cancel each other out, and then we're left with 0.04 molar plus X. And X is the concentration of the sodium hydroxide solution that we're adding. Now, with this, one thing that we need to come back to, and what principle we need to understand, is that we need to understand this part right there. If the pH equals the pKa, we know Henderson-Hasselbalch equation looks like this. A minus divided by HA. So in order for that statement to be true, then this term has to be 0. And that will be 0 when the A minus concentration equals the acid concentration. Okay, so that's what we're solving for, is when the concentration of acetate and the concentration of acetic acid are the same. So what we can do is, that's equilibrium, but now we can set it up as an equation and say we need to set those two sides equal to one another. And when you set those two sides equal to one another, we're operating under that idea right there. So if we solve for X, what would we do here? 0.134 molar. We will add or subtract these from both sides. And then we will add the X to both sides. And when that simplifies down, we end up with 0.094 molar equals 2X. Let's solve for x by dividing by both sides. And so what we have is that x is going to equal 0.047 molar. And that is of our hydroxide solution. Okay, so that's the concentration. Okay. That is the concentration, the final concentration of sodium hydroxide after we add X amount to it. So now we want to figure out, okay, well, how much of the sodium hydroxide solution are we going to add? And the concentration of it was what, 3 molar? So in order to do that, we need to understand that we have concentration initial, volume initial. Concentration final, volume final. So what do we want to figure out? We want to figure out the initial volume of our sodium hydroxide solution. We know that we started out at 3 molar. We just calculated from the X what our final concentration of that sodium hydroxide solution needs to be. And then what is our final volume? Well, we started with 4 liters plus the initial volume of the sodium hydroxide. And so we know everything. So when we look at this equation here, we know 3 of the 4. So when we plug all those numbers in, we have 3 molar. There's our variable that we're trying to solve for. Concentration final is 0.047 molar times the volume, the final volume, which was 4 liters, plus the initial volume of the sodium hydroxide solution that we added. Now when you look at that equation, we only have one variable. So all we have to do is solve for it. Okay, so in order to do that, we're going to have to distribute this in. So we have 0.047 molar times 4 liters plus a 0.047 molar times that, and that would equal 3m over VI. Not 3m times VI. Now we have two variables. We have one variable, but they're on both sides of the equation, so we have to combine like terms. All right, so what we're going to do is I'm going to go and bring this guy over to both sides. And let's just simplify that down. VI minus 0.047 molar times VI. And that's going to equal 0.047 molar times 4 liters. Okay. And then let's isolate or factor out a VI. So we would have 3m minus 0.047m. 0.047m times 4 liters. Now we can solve for V sub I by dividing both sides by 3m minus 0.047 molar to both sides. And that's going to be our answer there. 0.047 molar times 4 liters. 3 molar okay. You plug that all into your calculator. You're going to get a value of 0.06366 liters. Which, if we want that in milliliters, that would be 63.6 milliliters. And so that is the volume of the 3 molar sodium hydroxide solution that you would add to the 4 liters. And so what would our total volume be? Well, it would be 4 liters plus this value right here. So you can see it's 4.06 liters. Like, it didn't change the volume very drastically. But it did, in fact, change the volume. So this method right here accounts for that. Now, a more simplistic view or a simpler calculation is going to take a look at not worrying about the change in volume. So we're going to have the same equation, but this time, instead of using concentration, let's convert all the concentrations into moles. So our acid here was 0.134 molar, which is moles per liter. And let's times it by 4 liters because that's how much we have, and that's going to give us the total amount of moles. That's how many moles of our acetic acid we're going to have. And then if we do that to the acetate, we started out with 0.04 moles per liter times by 4 liters. It's going to give us 0.16 moles. So when we come here and draw our ice table, we can say, hey, we started with 0.536 moles. We're going to add X amount of that. We started out with 0.16 moles of acetate, and we don't need to worry about water. Now the change, well, kind of is the exact same thing as before. We're going to use hydroxide to deprotonate the acid. So we're going to use that, and we're going to gain a acetate molecule. When we look at equilibrium, we see that we have 0.536 moles minus X with 0.16 moles plus X. Now, in this case, what does X equal? That equals the moles of our sodium hydroxide solution. So we're not in concentration anymore, we're just dealing with moles. And we know that if the pH equals the pKa, then if the concentration of A minus has to equal the concentration of the acid in order to make that statement true, then we can also say the amount of moles would have to be the same as well. So since we're dealing with moles, we can set this equation now equal to one another. And now we solve for X. And I'm just going to give you the answer for this one. So if you take that equation right there and solve for X, you're going to get a value of 0.188 moles of our sodium hydroxide. That's how many moles we need to add to our 4 liters. So then, if we add that many moles, okay, what volume are we going to add? Because remember, our sodium hydroxide is in a solution. And so we use these values right here. If we have that many moles of sodium hydroxide that we need to add, then what's the concentration of the solution that we have? And we know that is 3 molar. And 3 molar is 3 moles per liter. So all we have to do is divide that. 3 moles per liter. And that's going to equal 0.06266 liters, which is 62.6 milliliters of our sodium hydroxide solution, of our 3 molar sodium hydroxide solution to be more precise. Okay, so when we compare those answers there, 62.6 mils versus 63. So both very, very close. One's more accurate than the other. But if you do either one of these on exam day, both would be counted correctly or counted for full points. And so I hope you guys find that helpful. If you have any questions, please let me know.